We are thorough with open chain hydrocarbons. Let's finally divert our attention to closed chain hydrocarbons and something new, alkyl group. Let's learn how it is. Now we remember hydrocarbons are divided into two types, open chain and closed chain hydrocarbons. Now these closed chain hydrocarbons are also called as ring chain hydrocarbons or cyclic hydrocarbons. We are not going to study the millions of cyclic hydrocarbons. We are just going to learn two examples. Example number one, cyclohexane, that is C6H12. And how would you draw a C6H12? So it is cyclo. It is a hex, hex meaning 6. So similarly, draw a 6-sided carbon. Ane meaning single bond, so you draw a single bond. Then you identify how many bonds are required to complete its stability. Every carbon has not one but two bonds. You have to look at both the sides. So 2 bonds for every carbon. So how many does it require? 2 more. How many hydrogens do we have? 12. How many carbons do we have? 6. Can we give 2 hydrogens to every carbon? Yes, we can. And if we do that, tada, cyclohexane. And you get 2 marks for drawing cyclohexane, and that is how simple it is. Similarly, benzene, C6H6. Now, carbon is 6. So you drew 6. Then you draw a single bond because it is a closed chain. Now what would you do? Hydrogen, the number of hydrogen is 6. The number of carbon is 6. So every carbon will have 1 hydrogen. But wait, if it has 1 hydrogen, just look at it. Carbon has only 2 bonds, meaning a hydrogen will have a double bond. Is it possible? No, it's not. Hydrogen has only 1 electron, so making a necessity to have a single bond with hydrogen. So, but there is a problem. There are only 3 electrons. Where did I say it is complete? So can I say if there are 3 bonds, 1 electron of every carbon is free? So free valence electrons I'm drawing for every carbon. So every carbon has free electrons. Can you see the crosses for carbon? Achha, what will happen if both the carbons are reactive on its side? So both the carbons will share and form a double bond. So if the double bond is formed, 2 electrons got insert. Achha, the next will it happen? No, because the double bond has to have 2 electrons from each carbon. Therefore, next would be a single and then would be a double. Next would be a single and then it would be a double, making a alternate single double bonding for benzene. So remember, cyclohexane single, benzene double. So this is how you draw a cyclic hydrocarbon. So let's study the first 10 members of the alkane family: methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and last one would be decane. Now you remember, I just wanted to remind you of the root words. So let us consider the first 4 members of the alkane family, that is methane, ethane, propane and butane. Now imagine, let's see the structure of methane. Now imagine if I were to remove 1 hydrogen. If I were to remove 1 hydrogen, what would happen? Can I say the CH3 would become reactive as 1 hydrogen electron has gone, so leaving behind 1 cross of carbon, making it reactive. So CH3 is reactive. On removal of 1 hydrogen atom from an alkane, we get an alkyl. So it means if I remove 1 hydrogen from methane, then CH3 is a methyl group. Similarly, the structure of ethane is C2H6 and looks something like this. So if I remove 1 hydrogen, can I say what I get back is a ethyl group? So if a methane can be converted into methyl, ethane into ethyl. So similarly, can I say a propane can be converted into propyl and a butane can be converted into butyl? Now what happens is, now you can see what is the general formula then, sir. Very simple. Alkane is CnH2n plus 2, right? Remove 1 hydrogen. Since alkyl group has 1 hydrogen less as compared to the corresponding alkane, CnH2n plus 2 minus 1. So the general formula of the alkyl group is CnH2n plus 1. So this is how methyl, ethyl, propyl, butyl are formed. And what is common? All of them are reactive. So we represented all the alkyl groups as a capital R as they are reactive. And if they are reactive, how many electrons do they want? They want 1 electron. So therefore, all the valencies of methyl, ethyl, propyl, butyl is 1. So let's consider this. I have methyl, I have ethyl, I have propyl, I have butyl. Let us consider the methyl group. The methyl group looks something like this. So methyl is CH3. the H atom removed can be replaced by some other element. Obviously, this carbon is reactive. Obviously, it is going to react. Can it react with the OH? Yes, it can, because OH has a valency of 1. Carbon has a valency of 1. And when they both react, they form something like this. So if a OH reacts in organic chemistry, OH group represents a group of compounds called as alcohols. So this, my dear friend, is CH3OH. Now can I say that CH3 can be replaced by any of the alkyl group? If I remove that methyl and put a ethyl, it's okay. If I remove that ethyl and I put a propyl, it's okay, because all the R's have valency 1 and OH has valency 1. So can I say R-OH is an alkyl alcohol of some sort? And what is the alkyl that we used? The alkyl that we used is methyl. So this becomes methyl alcohol. So CH3OH is methyl alcohol. Similarly, I can also use a ethyl alcohol, a propyl alcohol, a butyl alcohol, you name it, it can be done. Similarly, let's see a alkyl group R methyl with a chlorine. So if I have CH3, I can replace a Cl as I did for OH. So what is this methyl? Can I replace this methyl with the ethyl? Yes, I can. So R-Cl. So R is methyl, so methyl chloride, definitely. So similarly, can a ethyl chloride be formed? Yes, C2H5Cl would be ethyl chloride, propyl chloride, butyl chloride, as we go on. So let's study why we did this in the next module. Stay tuned, very important one coming up.